Welcome! In this session, we'll be exploring an exciting problem titled Unique Binary Search Trees 2. This problem is a great way to deepen your understanding of binary search trees and recursive tree building techniques. Stick around as we break down the problem step by step. In this problem, we are tasked with generating all structurally unique binary search trees, or BSTs, that can be formed using exactly n nodes, where the node values are unique integers ranging from 1 to n. The challenge is to return these trees in any order. For input, we will receive a single integer n, which will always be between 1 and 8, inclusive. The output should be a list of all possible unique BSTs, with each tree represented as an instance of the treenode class. The treenode class is defined with three attributes: val, which stores the value of the node, and left and right, which point to the left and right child nodes, respectively. Let's now explore an example to better understand how this works. For the input n equals 3, we need to construct all unique BSTs using the values 1, 2, and 3. One possibility is to use 1 as the root. In this case, the only option for the right subtree is to include 2 as the right child of 1 and 3 as the right child of 2. This gives us the tree where 1 is the root, 2 is its right child, and 3 is the right grandchild. Another option is to still use 1 as the root, but this time make 3 the right child and 2 the left child of 3. These two configurations represent structurally distinct BSTs, as the placement of the nodes differs. Let's look at more possibilities. Now, consider using 2 as the root. In this case, 1 becomes the left child, and 3 becomes the right child, resulting in a balanced BST where all nodes are symmetrically placed. Alternatively, if we use 3 as the root, we can create a tree where 2 is the left child of 3, and 1 is the left child of 2. Lastly, with 3 as the root again, we can swap the subtrees to make 1 the left child of 3 and 2 the right child of 1. These configurations complete all structurally unique BSTs for n equals 3. Let's solidify this understanding with a quick explanation. For n equals 3, we see that there are exactly 5 structurally unique BSTs. Each tree has a distinct arrangement of the nodes 1, 2, and 3, adhering to the properties of binary search trees. This means that for any node, the left subtree contains values smaller than the node, and the right subtree contains values larger than the node. Moving to a simpler case, consider the input n equals 1. Here, there is only one possible tree, which consists of a single node with the value 1. Since there are no other nodes, the tree has no left or right children. The constraints of the problem ensure that the input size is manageable, with n ranging from 1 to 8. This allows us to generate all BSTs recursively without running into computational limits. Additionally, each node in the tree must have a unique value from 1 to n, and the order of the output does not matter, as long as all unique trees are included. For edge cases, the smallest input, n equals 1, results in a single node tree, while the largest input, n equals 8, requires efficiently exploring every possible arrangement of left and right subtrees. It's also important to handle symmetry correctly, so trees with different root values but similar structures are treated as distinct. This ensures that the solution correctly accounts for all unique BSTs. To solve the problem of generating all unique binary search trees, we first considered a brute force approach. The intuition here is straightforward: generate all possible arrangements of numbers from 1 to n as binary search trees, and then filter out the invalid ones. For a tree to be valid, it must satisfy the BST property, where all nodes in the left subtree are smaller than the root, and all nodes in the right subtree are larger. This can be implemented using recursion to create all permutations of the numbers, construct the corresponding trees, and then check each tree for validity. However, this approach has a major downside. The number of permutations grows factorially with n, leading to a time complexity of O(n). Additionally, the overhead of checking each tree for validity adds even more computational burden. As a result, this method becomes infeasible for larger n, such as n equals 8, due to its exponential growth and complexity. Instead, we turn to an optimized approach based on recursive divide and conquer with memoization. The key intuition here is to systematically use the BST structure to build trees. By treating each number I in the range, 1, n, as the root, we divide the numbers into two groups. Those smaller than I form the left subtree, while those greater than I form the right subtree. Using recursion, we can generate all possible left and right subtrees, and then combine them with the root to construct unique BSTs. This approach avoids generating invalid trees entirely and is much more efficient. Memoization is used to store results of overlapping subproblems, ensuring we don't repeat work, which makes it computationally feasible even as n grows. The time complexity here is tied to the nth Catalan number, which grows exponentially, but memoization ensures we only compute each subproblem once. This optimized approach has several clear advantages. It is efficient, as it avoids generating invalid trees and is specifically tailored to the problem's requirements. It also scales well for the given constraints, where n is at most 8. Another potential approach is to use dynamic programming with tabulation. This is conceptually similar to the recursive method but works in a bottom-up manner. Instead of solving the problem top-down, we iteratively compute the number of trees for smaller ranges and build up to the full range, 1 is n. The implementation involves using a DP array where DP, I, j, stores all unique BSTs for the range, I, j. By computing DP, I, j, for increasing lengths of subarrays, we can combine smaller results to populate larger ranges. While this approach has similar time complexity to the recursive method, it comes with its own trade-offs. It is more memory-intensive since we explicitly store all intermediate results, and the implementation is generally more complex. As a result, while dynamic programming is a valid alternative, it may not be the most practical choice for this specific problem. Ultimately, we chose the recursive divide-and-conquer approach with memoization as the optimal strategy. This method aligns perfectly with the problem requirements of generating unique BSTs, as it directly leverages the structure of BSTs to systematically build valid trees. A key insight here is that the number of unique BSTs is determined by the Catalan number, and this recursive approach naturally mirrors the combinatorial structure needed to compute those trees. Memoization plays a crucial role in improving efficiency by avoiding redundant computations for overlapping subproblems. This makes the method both intuitive and computationally effective. Additionally, it is easier to implement compared to the dynamic programming approach, which requires more memory and involves managing a complex DP table. However, as with any approach, there are trade-offs to consider. The recursive method may encounter stack overflow issues for very large n due to its reliance on recursion. That said, this is not a concern here since the problem constraints limit n to a manageable size of at most 8. In summary, the recursive divide-and-conquer approach with memoization strikes a balance between clarity, efficiency, and problem-specific optimization. It avoids the inefficiencies of brute force and is less memory-intensive than dynamic programming, making it the ideal choice for solving this problem. To tackle this problem, we are tasked with generating all unique binary search trees, or BSTs, using numbers from 1 to n. A BST follows a specific property. For any given node, all nodes in its left subtree must have values less than the node, while all nodes in its right subtree must have values greater. This ensures the tree remains sorted at every level. Now, one possible approach is the brute force method. The first step in this approach is to identify all potential arrangements of the numbers from 1 to n by generating every permutation. For instance, if n equals 3, the permutations include 1, 2, 3, 1, 3, 2, 2, 1, 3, and so on. By considering every possible ordering, we ensure no potential configuration is overlooked. However, generating permutations is computationally expensive, with a time complexity of O(n). Once we have the permutations, the next step is to construct a BST for each one. This involves inserting the numbers into the tree sequentially, ensuring the BST property is maintained during each insertion. Let's take the permutation 2, 1, 3 as an example. First, we insert 2, which becomes the root. Next, we insert 1. Since 1 is less than 2, it becomes the left child of 2. Finally, we insert 3, which is greater than 2, so it becomes the right child. After constructing a tree, we need to validate it to ensure it satisfies the BST property. This is done using an in-order traversal, which should produce a sequence of nodes in ascending order. If the sequence isn't sorted, the tree is invalid. Valid trees are then collected into a result list for output. While this approach guarantees correctness, the construction and validation steps add further computational overhead on top of generating permutations. The final step in the brute force approach is to return the list of all valid BSTs. While this method is straightforward, it's not efficient. Generating all permutations alone is computationally expensive, and many of these permutations lead to invalid BSTs, resulting in wasted effort. However, there are still some useful takeaways. First, constructing a BST from a permutation guarantees that each tree structure is tied uniquely to that order. Second, validating the BST explicitly may not even be necessary if we ensure the BST property during construction. These insights pave the way for a more optimized approach that avoids the inefficiencies of brute force. To overcome the limitations of brute force, we use an optimized approach based on dynamic programming combined with recursion. The key idea is to build BSTs recursively by treating each number in the range as a potential root and generating its left and right subtrees from the remaining numbers. This eliminates the need to generate all permutations. First, we define a recursive function, generateTrees, start a end, which generates all unique BSTs using numbers in the range, start end. For the base case, when start exceeds end, we return a list containing a single element, none, representing an empty tree. Next, for each number I within, start, end, we treat I as the root. Left subtrees are generated by recursively calling the function on the range, start, I1, while right subtrees are generated from the range, I plus 1 is end. After generating the left and right subtrees for a chosen root, we combine them. For each combination of left and right subtrees, we create a new tree with the current root, attaching the left subtree as the left child and the right subtree as the right child. This tree is then appended to the result list. Finally, the function returns the list of all trees generated for the given range. This approach relies on a few key data structures, the recursive call stack, which manages intermediate states, and a list to store the resulting trees. Dynamic programming helps optimize the recursion by storing results for previously computed ranges, avoiding redundant calculations. The time complexity of this approach is tied to the Catalan number for n nodes, which grows as O, 4 to the power of n/n caret, 3 halves. Space complexity includes O, n, for the call stack and additional space to store the resulting trees. Lastly, we need to account for edge cases. If n is 0, there are no numbers to form a tree, so we return none. When n is 1, the only possible tree consists of a single node. For larger values of n, efficiency becomes critical, and memoization ensures we avoid redundant computations. To illustrate, consider n equals 3. The algorithm generates trees with roots 1, 2, and 3. For each root, its left and right subtrees are recursively constructed from the appropriate ranges of numbers. The final output includes all valid combinations, resulting in 5 unique BSTs. Examples include a tree with root 1, where the right subtree contains nodes 2 and 3, or a tree with root 2, where the left subtree is 1, and the right subtree is 3. This systematic generation ensures every possibility is explored efficiently. Here, we start by defining a simple tree node class to represent the structure of each node in our binary search tree. Each node has a value, along with pointers to its left and right child nodes. The generateTrees method is where the solution begins. The method takes an integer n, which represents the number of nodes we want in our binary search trees. If n is 0, we simply return an empty list since no trees can be formed. The core of the implementation lies in the helper function build_trees, which recursively generates all possible unique BSTs within a given range, defined by start and end. If the start value exceeds the end value, it means we cannot form any valid tree for that range, so we return a list containing a single none value to indicate an empty subtree. Next, we initialize an empty list called all_trees to store all unique trees for the current range. We then iterate through each possible root value within the range, from start to end. For each root value, we recursively generate all possible left subtrees and right subtrees by calling build_trees on the respective subranges. This is the essence of the divide and conquer approach used here. Once we have the lists of possible left and right subtrees, we use nested loops to pair each left subtree with each right subtree. For each such combination, we create a new root node with the current root value. We then assign the left subtree to the root's left child and the right subtree to its right child. This root node represents one unique binary search tree, so we append it to the all_trees list. After exploring all possible root values within the range, we return the all_trees list, which contains all valid BSTs for the given range. Finally, in the generateTrees method, we call build_trees with the range 1 to n and return its result. This ensures that all possible unique binary search trees with values from 1 to n are generated and returned as a list. This approach efficiently combines recursion and backtracking to systematically explore all possibilities while maintaining the BST property. Here, we start by defining the treeNode class, which represents each node in our binary search tree. It has three fields: val to store the value of the node, and left and right to point to its left and right child nodes, respectively. The class also includes multiple constructors for flexibility when creating nodes. Next, we move on to the solution class, where the main logic resides. The method generateTrees is our entry point. It takes an integer n and returns a list of all unique binary search trees that can be constructed with values from 1 to n. If n is 0, meaning there are no values to form a tree, we return an empty list. Otherwise, we call a helper method, buildTrees, which generates all possible BSTs for the specified range of values. This helper method is key to our solution, as it recursively constructs trees for all combinations within the given range. The buildTrees method starts by creating a list to store all possible trees for the given range. If the start value exceeds the end value, we add null to the list, representing an empty subtree, and return it. This forms the base case for our recursion. Now, for each value in the range from start to end, we treat that value as the root of the current tree. We then recursively generate all possible left subtrees using values less than the root and all possible right subtrees using values greater than the root. Once we have these lists of left and right subtrees, we combine each left subtree with each right subtree, attaching them to the current root node. This ensures that all combinations are considered. Finally, the newly constructed trees are added to the list, and once all values in the range have been processed, we return the list of trees. This recursive approach ensures that every unique BST is generated efficiently. In this problem, we aim to generate all unique binary search trees, or BSTs, that can be formed using values from 1 to n. A binary search tree is a type of tree where, for every node, all the values in its left subtree are smaller, and all the values in its right subtree are larger. For example, when n equals 2, we start by considering each number in the range as a potential root. If we choose 1 as the root, there are no valid numbers for the left subtree, so it is represented as none. For the right subtree, we calculate trees using the range 2 to 2. With 2 as the root of this subtree, both its left and right subtrees are empty, giving us a single tree, 2 with no children. Finally, we combine this right subtree with the root 1 to form the tree 1 with 2 as its right child. This gives us one possible unique BST for n equals 2. Now, if we choose 2 as the root, we calculate the left subtree for the range 1 to 1. Here, 1 is the only possible root, and both its left and right subtrees are empty, resulting in the tree 1 with no children. For the right subtree of 2, there are no valid numbers, so it is represented as none. Combining the left subtree 1 with the root 2 gives us the tree 2 with 1 as its left child. This means that for n equals 2, we have two unique BSTs, one where 1 is the root and 2 is its right child, and the other where 2 is the root and 1 is its left child. When n equals 3, we start by considering 1 as the root. The left subtree has no valid numbers, so it is none. For the right subtree, we calculate all possible trees for the range 2 to 3. If 2 is the root of this subtree, it has no left child, and its right child is 3 with no children, forming the tree 2 with 3 as its right child. Alternatively, if 3 is the root, it has 2 as its left child and no right child, forming the tree 3 with 2 as its left child. Combining both possibilities with root 1 gives us two trees, one where 1 has 2 as its right child, and another where 1 has 3 as its right child. Next, we choose 2 as the root. For the left subtree, we calculate trees for the range 1 to 1, which results in the tree 1 with no children. For the right subtree, we calculate trees for the range 3 to 3, which gives the tree 3 with no children. Combining these, we get the tree 2 with 1 as its left child and 3 as its right child. Finally, when 3 is chosen as the root, we calculate the left subtree for the range 1 to 2. This produces two trees, one where 1 is the root and 2 is its right child, and another where 2 is the root and 1 is its left child. The right subtree is none. Combining these possibilities with root 3 gives us 2 more trees. Altogether, for n equals 3, we have 5 unique BSTs. This process works through recursive calculations of left and right subtrees for every possible root value. By combining these subtrees, we generate all unique BSTs for a given range of numbers. The base case ensures that when the start value exceeds the end value, we return none to represent an empty subtree. Ultimately, for any value of n, the function will return a list of tree roots, each representing a unique BST. This systematic approach guarantees that all possible unique BSTs are accounted for. The time complexity of the generateTrees function is driven by the number of unique binary search trees, or BSTs, that can be formed for a given n. This count is determined by the Catalan number, which is a mathematical formula used to calculate the number of structurally unique BSTs. Specifically, the nth Catalan number is given by the formula C, n, equals 1/n plus 1 multiplied by the binomial coefficient 2n choose n, or equivalently, 2n. Divided by n plus 1. Asterisk n. For each value of n, the function recursively generates all possible left and right subtrees. For every unique combination of these subtrees, a new tree is constructed, which involves iterating through all potential root values. As a result, the number of unique BSTs that can be generated is C, n, and the cost of constructing each tree depends on the operations to combine left and right subtrees. When we factor in the asymptotic growth of the Catalan number, which is roughly 4 to the power of n/sqrt, n, the overall time complexity of the function becomes C, n, asterisk n, or approximately 4 to the power of n/sqrt, n, asterisk n. Now, looking at the space complexity, there are 2 main components to analyze. First, the recursive call stack. Since the recursion depth is at most n, this contributes n to the space complexity. Second, we need to account for the memory required to store all the generated trees. Each recursive call generates all unique BSTs for a specific range, and the total number of trees is proportional to the Catalan number, C, n. Each tree consists of n nodes, so the memory required to store all these trees is proportional to the product of the number of trees, C, n, and the number of nodes per tree, n. This results in a storage requirement of C, n, asterisk n. Combining these 2 components, the overall space complexity is C, n, asterisk n. When we substitute the growth of C, n, this simplifies to approximately 4 to the power of n/sqrt, n, asterisk n, which aligns with the time complexity. To better understand the efficiency of this solution, let's compare it to a brute force approach. A naive method would involve generating all possible permutations of n nodes and checking if each permutation forms a valid BST. This approach would have a factorial time complexity, n, which is drastically worse than our optimized solution. By contrast, the recursive approach leverages the structure of BSTs and the properties of the Catalan number to generate only valid trees. This reduces the time complexity to 4 to the power of n/sqrt, n, asterisk n, which, while exponential, is far more efficient than factorial growth. The key reason for this improvement lies in the combinatorial nature of the problem, where the number of valid BSTs is directly tied to the Catalan sequence. In terms of best, average, and worst-case scenarios, the complexity remains the same across all cases. This is because the algorithm always explores all possible combinations of left and right subtrees regardless of the input. Therefore, the time and space complexities consistently align with 4 to the power of n/sqrt, n, asterisk n, especially as n grows large. When solving this problem, there are a few common mistakes to watch out for. First, it's critical to validate the binary search tree property. This means ensuring that all nodes in the left subtree are smaller than the root, while all nodes in the right subtree are larger. If this is not properly enforced during tree construction, the resulting trees may not be valid BSTs. A good practice is to recursively validate these constraints as you build the tree. Another frequent issue is neglecting the presence of overlapping subproblems in dynamic programming-based approaches. Failing to reuse pre-computed results can lead to redundant calculations, making the solution inefficient. Using memoization or a bottom-up dynamic programming strategy can help avoid this pitfall. Additionally, incorrect handling of base cases, such as when there are 0 or 1 nodes, is another common error. These edge cases are essential for completeness, and neglecting them can lead to incorrect outputs. Ensuring that your recursive or DP solution includes robust base case handling is key to solving the problem effectively. Another mistake to be aware of is misunderstanding the output format. For problems requiring you to return a list of all unique BSTs, it's important not to confuse this with simply returning the count of trees or providing an incomplete list of structures. Carefully reading the problem statement and ensuring your output matches the expected format, such as generating full tree structures, not just their count, is vital. Furthermore, inefficient tree construction can also be a major bottleneck. Repeatedly constructing or copying tree structures within recursive calls can unnecessarily inflate both time and space complexity. To address this, look for ways to optimize tree construction, such as reusing nodes or referencing shared subtrees whenever possible. By adhering to these principles, you can avoid common inefficiencies and ensure your solution is both correct and optimized. To perform well on this problem in interviews, it's important to focus on a few key insights. First, understanding recursion and dynamic programming is essential. You should aim to break the problem down into smaller subproblems, for instance, determining how many unique BSTs can be formed with a specific range of nodes. Recognizing patterns in these types of problems is also valuable. Many problems involving unique combinations or arrangements, such as this one, often rely on recursive tree construction, dynamic programming, or even leveraging Catalan numbers. Be ready to discuss optimization strategies, such as the trade-offs between recursive and iterative DP approaches, particularly in terms of time and space complexity. Additionally, interviewers may explore follow-up questions or variations, such as asking you to count the number of BSTs instead of generating them, or to impose additional constraints, like ensuring the trees are height-balanced. Finally, related problems like LeetCode 96, 108, and 894 can help you draw connections and deepen your understanding of tree-based solutions. There are also alternative approaches to solving the problem, each with its own trade-offs. Recursive backtracking is a straightforward method, as it's easy to implement and intuitive for small inputs. However, it can be highly inefficient due to redundant calculations, especially as the input size increases. Using dynamic programming with a top-down memoization approach can address this inefficiency by storing results of subproblems to avoid repeated computations. The trade-off here is the additional memory required for memoization. A bottom-up dynamic programming approach, on the other hand, builds solutions iteratively from smaller subproblems up to the desired size, often making it more space-efficient. However, implementing this method for tree construction problems can be more complex. Lastly, the combinatorial approach leverages the Catalan number formula to directly compute the result. While this is extremely efficient for counting the number of BSTs, it doesn't generate the tree structures themselves, limiting its usefulness for tasks that require the actual tree outputs. Understanding these approaches and their trade-offs can help you choose the most appropriate method based on the problem requirements. Great job! We've successfully tackled the unique binary search trees 2 problem. You now understand how to generate all possible BSTs and the recursive approach behind it. Remember, practice makes perfect, so keep challenging yourself with more problems like this. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!